So in most reinforcement learning settings, we reiterate between two different tasks, namely policy evaluation, which is where we evaluate the policy that we then want to follow, and then policy improvement, where we improve upon that policy. In the policy evaluation stage, we estimate the Q value function, and this can be done through a number of different methods. So one would be Monte Carlo, and the other would be temporal difference learning, for example. In the policy improvement stage, however, we update the policy that we have with respect to this action value function Q. And one way you could imagine doing that is just maximizing the entire function Q and then selecting that as your policy. That sounds better than it is, or it's very tricky to do so. The reason why is because you're trying to maximize a function that could be multi-dimensional and then in a continuous action space, for example, and that will be very hard. So one way you could tackle this problem without maximizing all of the action space is to use greedy maximization and go in the gradient direction. So if you follow your gradient, you're locally going to be following the path that leads you basically ascending this action value function, which is again then an approximation of the actual action value function because you in turn just estimated it. And then you follow that upwards and you keep reiterating, so improving your Q value function and then improving your policy based on that function. So looking in more detail at the deterministic policy gradient, the performance objective then would come out as rho, which is our distribution of states, and then the reward for a state in an action. But now this time we see that we have mu of s in the expression there in the integral, the top one. This mu is indicative of the fact that we're using our policy now to base or to guide our decisions. So we know what the action is going to be. The action is going to be deterministic policy mu of the state s. And because it's deterministic, this mu, we can input it as a single value and we know what it's going to be. And this can again then be written in the form of an expectation. And then we have the reward inside. So this could then be sampled with, for example, Monte Carlo. When we then optimize this, we use gradient ascent technique. And so we differentiate. And again, we can see that the state distribution term comes out unaffected in the expression. So there's no need for differentiation there. And it can also be written in the expectation form. So once we've sampled this by approximating Q, we can then improve upon the strategy that we selected. If we compare this for the non-policy case, we see at the bottom right, where it's far from, or there's definitely a difference between them and they don't look that similar. However, it is the case that the deterministic policy gradient is in fact the limit of the stochastic policy gradient. So the stochastic policy gradient is the one that we can see at the bottom right here, and the deterministic one is the one which is slightly above, which we're discussing. And if you're thinking about what we're doing here, we have one policy which is deterministic, and then we get one result. We have one policy that is stochastic, and then we get another result. And the policies approach each other. So I mean, if you consider the stochastic policy, but then you let the variance, let's say, of that policy go to 0. So imagine having two states like the road that we talked about before. If you go left or you go right, you have some sort of variance there because you're not always picking the same action. But if you shrink that variance down so that in the end you only take one action all the time, then you essentially get the deterministic policy. So you have a natural way of moving from a stochastic policy to a deterministic policy. And it turns out that the same sort of relationship or the same limit exists in the case of the performance objectives, which are the J variables. And that's far from obvious. So we have two different policies, and just because the variance of one goes to 0 doesn't mean that a completely unrelated, or well, not completely unrelated, but a completely different quantity associated with that policy would also approach the corresponding value for the deterministic case. But there is a result in the paper that tells us that this is the case. There's a proof and stuff in the appendix, but we won't go through that here. It's mainly for intuition. So in general, the deterministic policy gradient is the limiting case of the stochastic policy gradient. And yeah, it doesn't really look that way from the expressions we saw on the last slide, but that is indeed the case. The result then, so the fact that these two policy gradients approach each other shows that a number of results, so a few of them are listed here, natural gradients, for example, actor-critic, episodic batch methods, and so forth, they're also applicable to deterministic policy gradients. So the results are sort of based on those limits or on the existence of these gradients. And since one is the limit of the other, the results transfer to the deterministic case as well, which saves a lot of trouble and makes it possible to leverage all the framework well, a lot of the framework in the stochastic case, even in the deterministic one. So those are good news. Okay, so if we're looking at an on-policy deterministic actor-critic, so notice that I said on-policy now. So for a start, let's consider when we're actually acting according to the policy that we're learning. So it gives bad exploration naturally. Like it's not necessarily something you would do if you're in the situation of trying to solve a problem. The reason being that you want more exploration so that you can sort of have a lot of exploration, so you gather data from lots of different paths that you could potentially follow, and so that you find optima that might otherwise be shielded or out of view, let's say. But for the actual policy that you want to be following, then you want that to not be as exploratory. So that's why off policy could be a good idea, but for the sake of beginning this argument, let's start with on policy. So the critic then estimates the action value function, and we have something that resembles the action value function to the right here. So we have some sort of surface area, or it can be in more dimensions as well, so it's not very easy to sort of visualize, but anyway, we have some sort of function like this that we approximate. So we have a parametric, parameterized function approximator that tries to capture the shape of this actual Q value function, which we at the start don't know. And then it's the job of the critic to then optimize the parameters such that we climb this, the slope. And for this particular on-policy algorithm, we're using a Sarsa-based critic or actor-critic algorithm. So we can see basically what the updates become for the various components. And this is the standard Sarsa update. We won't go into the details of what the various different terms here are. I mean, this is the TD error, for example. This is the Q function parameters, and this is the policy parameters. But we won't go into granular details on exactly what those interpretations should be. But now that we've seen the on-policy case, let's also look at the off-policy deterministic actor-critic. So now the difference is that the target policy mu is learned from a behavior policy pi. So we're following a policy that that is our behavior, but we're trying to create a target policy based on that. Similar performance objective as before. So we have the distribution of states, and then the value function that we're integrating over the total state space. And the value function can be written out as the Q value function with the deterministic action, because we know in each state, if we want to evaluate how good a state is, the value of that state is just going to be the Q value if we act according to the policy that we set for ourselves, because that is 100% of the time going to be how we act, and so it's also going to reflect the value that we get back. So the off-policy gradient, then, if you do the differentiation, comes out to be the expression that we see here, and they drop one term in the paper, which is not really affecting the overall results, but nevertheless, I noted it in the graph here. For details, I would refer to the paper for exactly why they're dropping it and so forth. But this can be written as an expectation, and then we have a nice expression for the policy gradient in the off-policy case as well, or the performance objective gradient, sorry, in the off-policy case. Okay, so based on this, you can then derive an algorithm as well in the off-policy case for a deterministic actor-critic, and that comes down to the acronym OPTAC, and it's based on Q updates, and it's very similar to what we saw in the on-policy case. The difference then being that instead of the A, which was currently or previously present in in this parenthesis next to the Q value, we have a mu of the state. So that is the action we're going to take. Because we're following a deterministic policy, the action is simply replaced by the policy of the state. Okay, and one thing to note is typically you would use importance sampling for both actor and critic when you're doing the off policy case. However, since this is a deterministic case, it's a bit special. So the deterministic policy gradient means that, or because we're using a deterministic policy gradient, we don't need an action integral, because you would normally integrate over all the actions that you can take, but we can only take one action because our policy is deterministic. So even if you integrated over all the actions, the integral would simply be a delta function, and so that would integrate. It's just a point mass in the sense of an integral. So you don't need that action integral, and therefore no actor importance sampling. Also, because we're using Q learning here, there is no critic importance sampling required. So for this algorithm, you would actually be fine without using it.